Look at the path of a satellite in orbit, or a projectile launched across a field. You're watching physics carve a precise curve through space. To track where any of these objects will land, mathematics relies on identifying a specific geometric shape, the parabola. This chart shows that exact physical trajectory mapped onto a rigid coordinate system. Notice the sweeping curve crossing the horizontal x-axis in two places. We call these two precise locations the roots. They represent the exact moments the curve hits zero. Every parabola can be represented by a master equation, ax squared plus bx plus c equals 0. If we can solve this generalized equation to find its roots, we gain the mathematical power to map the exact landing point of any parabolic curve in the universe. Solving for an unknown variable is usually straightforward. Take a simple linear equation, like 2x plus 4 equals 0. You subtract 4 from both sides, divide by 2, and the numbers strip away. The variable x is perfectly isolated, but look closely at the quadratic equation. The unknown variable x exists simultaneously in two completely different states, squared and linear. These two states are mathematically stubborn. You cannot simply combine an x squared with an x. If you try to isolate the variable by dividing the entire equation by x, it cancels out in the middle term, but ends up trapped beneath the constant c. You create an endless loop. Shuffling numbers across the equal sign will not work here. To extract x, we have to force this equation into an entirely new structural shape. The first step is to strip away the clutter so the squared term stands completely alone. We do that by targeting the leading coefficient, a. We divide the entire equation piece by a. The leading a cancels out, leaving us with a normalized equation, x squared plus b over a times x plus c over a equals 0. The constant term at the end, c over a, contains no variables. It is mathematical noise that we need out of the way. We subtract it from both sides to push it across the equal sign. The unknown variables are now quarantined on the left side of the equation. We have cleared the board for a physical, geometric transformation. You may have heard the phrase, completing the square. It is highly literal. We are going to build an actual, physical shape. Here is a model of our first algebraic term. This square has sides of length x, meaning its total interior area is x squared. The next term is a linear value multiplied by x. We can draw this as a rectangle. It has a height of x and a width of b over a. To build a symmetrical shape around our base square, we take this rectangle and cut it exactly in half. The height of these two new slices remains x, but because we halved the width, each piece is now b over 2a wide. We attach one of these rectangles to the right edge of our main square. We rotate the other and attach it to the bottom. By converting algebra into area, we have constructed an L-shaped figure that is visibly close to being one large perfect square. Looking at the right side of the screen, you can see the problem. There is a literal void in the bottom right corner preventing this shape from closing. We know the exact dimensions of this missing piece by looking at the adjacent rectangles. It requires a width of b over 2a and a height of b over 2a. Multiply those together, and the area of the missing block is the quantity b over 2a squared. The rules of algebra dictate strict balance. If we add new area to the physical shape, we must add that exact same mathematical value to both sides of our equation. So we add the squared term b over 2a to the left side and to the right side. The left side of our equation now perfectly mirrors the complete unified square area model. It is a single shape with side lengths of x plus b over 2a. Because of this, we can collapse the entire sprawling left side of the equation into a single factored binomial, x plus b over 2a all squared. By identifying and filling that physical gap, the separate incompatible variables of x squared and x are forced into a single measurable term. Isolating the right side gives negative c over a plus b squared over 4a squared. To combine these fractions, we multiply the first by 4a over 4a. The numerators then snap together to form b squared minus 4ac. This numerator cluster is the discriminant. Its value determines the number of real roots, telling us if the parabola crosses the x-axis twice, once, or not at all. With the right side clean, we execute the critical move to rescue x. Taking the square root of both sides fractures our perfect square and creates two valid realities, a positive result and a negative one. That resulting plus or minus symbol perfectly mirrors the physical world. It explains why a parabola crosses a flat line in two distinct places. Notice the left side. The exponent is gone. X is finally free, attached only to a simple constant, plus b over 2a. The very last move is subtraction. We move b over 2a to the right side, completely isolating x. Taking the square root of the denominator earlier left exactly 2a. Because both fractions share this exact base, we combine them. X equals negative b plus or minus the square root of b squared minus 4ac, all over 2a. The quadratic formula stands as the ultimate, inevitable endpoint of manipulating a generalized curve through pure structural geometry.